Okay, so now you have two tasks. One is S, does it span the space? The first, that's the question, does it span the space, and are the vectors linearly independent? Now, if you want to sort of only do the Gaussian's method once, you want to do the span the space thing first. I mean, in a homework problem, I might ask you to do both, independently, or to do one or the other. But if you just wanted to get to the answer, like if you were asked, is this a basis? Then what you would first do is say, well, we need to take an arbitrary or typical vector in R3C. So we would choose, let's say, is this a basis? Well, let's first, so the plan is A. Let me use a lowercase a for some reason. Check whether span of S equals RC3. Now it's clear that any linear combination of these vectors is in R3C, right? It's like obvious, it's like clear. Well, how do we want to check that this is equal? Well, you want to, in other words, if you have two sets that are equal, you have to know that the span of S is a subset of RC3, and RC3 is a subset of the span of S. I mean, they're the same set and the same vectors. They're both vector spaces, but they're going to be the same vector space. We have to show that the span of S is in RC3, right? And then we have to show that RC3 is in the span of S. We know they're both vector spaces. So if we can show the subset, if we can show that they're subsets, they're going to be the same vector space. Now this one's obvious, right? Because if I take any linear combination of these and add them up, they're going to be a three-component vector. They're going to be in here. So this is obvious, right? Or clear. It's a move from your definition of a span. Okay, let me write that up. Let me. Is immediately clear. That is, you can see that it's true. From the definition of span of S. I mean, it might not be clear to you, right? And you might not see that it's true right away. But if you realize, once you realize that the span of S equals the set of, say, X 1, 1, 1 plus Y times 2, 0, 1 plus Z times 1, 0, 2 X, Y, Z, members of R, you can see, well, any one of these is going to be a three-component vector. So it's going to be one of these, right? This, because this 111 is a member of R3C, 201 and 102 are. If I multiply any of them by numbers, because it's a vector space, those have to be vectors in a space. And when I add two vectors, they have to be a vector in space. Otherwise, this wouldn't be a vector space. So just for the properties of the fact that I've chosen a subset of R3C, this is a subset of R3C. So is that okay with you guys? So the other one is more, the other way is the one you have to check. Because that's the one that might fail. In other words, you have to check, is C3 a subset of the span of S, right? So what we have to do is, what this means is, what the subset means is, if X, Y, Z is a member of RC3 um, for any X, Y, and Z, then it has to be that X, Y, Z is a member of the span of S. So that's what subset means. So the question is, well, so what you do is you suppose the premise is true here, and since it's for any X, Y, Z, then you say, okay, well, let's, if it's true for anyone, let's pick an arbitrary one. So you suppose that X, Y, Z is a member of RC3. For some, you could put a little a on here to indicate that you're choosing an arbitrary one, right? So it would be a little bit clear that this is any X, Y, Z, you choose one. Suppose for arbitrary XA, YA, and ZA. Then we have to show is, you have to show that this is true. That this vector XA, YA, ZA is a member of the span of Z. Okay? Well, it's going to be a member of the span of S, not Z. It's a span of S. If you can find, let me change this just so it's not so confusing. We have to find, let's put A, B, and C up here, because the X, Y, Z is just arbitrary variables, and the problem here is, this isn't ideal, but maybe the point is that these A, B, and C can be any numbers, right? So they're really variables. But the point is that, or maybe I should leave these. I'm sorry for my last minute. I'm going to leave this as before. So if you've been following closely writing notes, then your notes are a mess now. So we have X, Y, and Z, but down here, what I'm going to choose is I'm going to choose an arbitrary one, A, B, and C. Okay, so I've chosen arbitrary vector A, B, and C. I could leave it as X, A, Y, B, X. I could choose X, A, Y, A, Z, A, but then that's like using subscripts, and it could get sort of confusing. And maybe this is a particular arbitrary one, and we want to show that A, B, C is a member of the span of S. Okay? Well, to be a member of the span of S, we have to find X, Y, and Z. So some linear combination here is equal to this. To do this, we have to find X, Y, Z such that X times 1, 1, 1 plus Y times 2, 0, 1 plus Z times 1, 0, 2 equals A, B, C. Right? This is saying this would show that this vector ABC was in the span because we've written it as a particular linear combination of the basis vectors. Okay, so it's the right. I mean, so this I've written it. Maybe writing it, stating all the logic precisely can also be very confusing because it's too much detail, right? The take-home message is you want to show that any vector R3C is in the span. So you choose any arbitrary vector ABC, and you have to find X, Y, Z to exhibit it as a member of the span of S in the linear combination of X. So what this means is this is equivalent to solve this linear system, right? So basically, if you started up here with the problem at the beginning, is this a basis? And you wanted to check that this set spanned the space, you would jump down here and say, choose a vector ABC of R3. We need to find XYZ so that this is true. But behind that is all this sort of logical technology that makes everything precise, right? In some way, you might say that like this step here is called universal specification. I think this appeared in, it's one of the defects of the text. It doesn't make universal, this logical move from for every XYZ to choose an arbitrary one explicit. But okay, so then let's say if we can, then so from this form, we can immediately write down the augmented matrix of this linear system, which is 1, 1, 1, 2, 0, 1, 1, 0, 2, A, B, C. Okay? So if you think of this from a problem point of view, I'd give you a set of vectors, and you would set up the linear system, then solve it with Gauss's method the normal way that you do. And the one weird thing is, like this is the X column, the Y column, and the Z column, and these A, B, and C. I wanted to use A, B, C here because these are, for this linear system, these are constants, right? Even though they're arbitrary constants, meaning that you can make them any values you want for the linear system. Here, they're constants. Okay, so you have to get used to like treating these as like it could be 1, 2, they could be 4, 5, 6, some particular values. So think of them as some particular values, and you're trying to solve this linear system. Well, we'd have to go through. Let's go ahead and do this to see what the answer is, and we do minus row 1 plus row 2 and minus row 1 plus row 3 to clear this first column here. And so we'd have 1, 2, 1, A. And the first one is minus 1 plus 1 is 0. Minus 2 plus 0 is minus 2. Minus 1 plus 0 is minus 1. And minus A plus B is the same as B minus A. We've subtracted this one from the lower one, okay? Since we don't know what B and A, this is some number, we don't know what they are, but it's just a number, okay? Then we have to do the second one, minus row 1 plus row 3, we get a 0 there. Minus 2 plus 1 is minus 1. Minus 1 plus 2 is 1, and then we have C minus A down here. Okay, and then we're almost at echelon form because we just need to clear the Y column, to clear this variable here, so we can do 1 half, or we need to do minus 1 half row 2 plus row 3, because that's going to give you a 1 plus a minus 1. That's what you need to clear that one. So we leave everything else the same. We only have to mess with the third row here. Well, minus 1 half times minus 2 is 1, and 1 plus minus 1 is 0 here. And then we have minus 1 times minus 1 half is 1 half. 1 half plus 1 is 3 halves, 1 plus a half. But then we have to do it over here too. We have here C minus A plus minus a half times this. We have to have minus 1 half B minus A, which is awkward because it's so getting unwieldy. So you'd want to usually leave more space here. But we can see right away that there is one solution here, right? Because all three variables are leading, X, Y, and Z. Now, so what that means is, for example, let's look just at the last one. That means the equations are 3/2 z equals c minus a minus 1/2 b minus a, which we could simplify if we wanted to being c, and there's going to be a minus 1/2 b, but then we have minus 1/2 times minus a is plus 1/2 a minus a, so that's going to be minus 1/2 a, and then we have to divide through by this, but you can see we have a value for z, and then the equation we're going to be able to solve minus 2y minus z equals b minus a. So we're going to be able to say, well, minus 2y equals b minus a plus z. But then we know that z is 3/2 z is this. So we could simplify this as b minus a plus 2/3 to cancel out the 3/2 of this whole. So we want to put in here 3/2 z, and then we'll get out 2/3 c minus 1/2 b minus 1/2 a, and so it's getting tedious algebraically, but you can see that what's going to happen is I've got a value for any, so you choose a, b, and c, and I can tell you what z is, I can tell you what y is, and then the same thing's going to happen with x plus 2y plus z up here equals a, and that's going to be a is equal to a minus 2 times, what's going to be a minus 2y. Well, minus 2y is plus this whole thing here, so it's going to be b minus a plus 2/3 c minus 1/2 b minus 1/2 a, and then we'd have to do minus z, which would be minus 2/3 c minus 1/2 b minus 1/2 a. And you can see, this thing is here, this form doesn't really matter. It just matters you have a solution. So in one sense, you can stop here and say, okay, all variables are leading. So there is, and there's no contradiction, so there is a solution. And I just exhibited, you can go through and find the explicit form if need be. So that's why it's tedious because of the A, B, and C here, right? And so you'd hope that on a test or demonstration or concept check that I would choose my numbers more wisely so that so that some of this wouldn't be so complicated.
Just to check, because there is a solution or at least one solution, then that means S is a basis of our.
We're not a basis yet. What we've chosen, what we can show yet, what do we know? What do we know? Because the calculation is long enough that you've forgotten what was happening. What was happening was we were checking whether R3C was in the span of S. So we were checking whether S spans the space, right? So, and we know that everything in the span of S is in R3C. So we're just checking, can I write any vector in R3C as a vector in the span of S? And the answer is yes, because we can solve the system. So from this, we can jump over and say, we know that S spans the space R3C. And so the point is, I've exhibited here, I could simplify these, and then you could say, well, you give me an ABC, and I'll tell you what X, Y, Z are, that allows you to write that vector ABC as a linear combination of S. So we know that S spans the space. Okay, now, to be a basis, we'd have to check now to check linear independence. Well, what that means is we take a linear combination, 1, 1, 1. We take a linear combination, let's say x plus y plus z, and we say suppose this equals 0, 0, 0, right? This is the test. We suppose this, and then we must show that if this is true, that it's not x, that x equals y equals z equals 0. Now, if this is true, if successful, then S is linearly independent and S is a basis. Okay? Okay, so now, the thing is this, we could go through and say, well, this linear system has an augmented matrix, 1, 1, 1. 2, 0, 1, 1, 0, 2, and 0, 0, 0. But you notice that this is a special case of this augmented matrix for the previous system. It's the special case when A, B, and C were 0. Right? So you can say from previous check above, we could say that, well, we know that here that, see, 3 halves z equals this thing. So C is 0, B is 0, Z is 0. So we know that we can say that we know that 3 halves z equals 0. So Z is 0, right? And then from the second one, this y equation, we can say, well, we know that A and B is 0 and Z is 0. That's going to mean, we know that minus 2y plus z equals 0, or equals, see, what's it, minus 2y minus z equals b minus a, but because b and a are 0, those are 0, and since z is 0, we know that y is 0. And then the last equation for x was, well, x plus 2y plus z equals a, x plus 2y plus z equals a. Well, a is 0, z is 0, y is 0, therefore x is 0. So we've shown that this assumption, therefore, S is composed of linearly independent vectors. Okay, so that's sort of the procedure you'd follow in solving one of these problems. And you wouldn't need to write I'm being more expansive than what you'd need to write, okay? So I've tried to make it sort of plausible, like you might not need to write out things explicitly. On the other hand, if you want to check linear independence, right? It can be that vectors span the space, but are not linearly independent. So so it could be that this is true. It spans the space, but it might not be because there could be a free variable up here, right? So there is a solution. It's really that there's no contradictions. I could have gotten a free variable up here. If I got a free variable up here, when I come down here, I'm not going to be able to show this, so they wouldn't be linearly independent. So in that case, you might, but then still, you might not need to find this. You might be able to say, okay, well, if these ones are 0, I have a free variable, so I just choose values. I can find a counterexample and find a vector that's I can find a linear combination that's not equal to 0. So it can be that vectors are linearly independent but don't span the space, or that they span the space but don't are not linearly independent, or they might span the space and also might not be linearly independent. See, from knowing one, you don't know anything about the others. You just have the tools to figure that out. Okay, so there is sort of like the big picture problem. Let me